Awesome. Yeah, so this morning we have Sam Kelly, who's speaking, and Sam is the Conservation Technology Program Manager at Conservation X Labs. He's actually a mechanical engineering graduate from Duke, and he focuses on identifying and developing new technology opportunities with impacts in conservation. And as an engineer, he has expertise in both like physical, electronic, and hardware design for conservation technology projects. And I think today he's going to be talking a bit about one of the larger projects at Conservation X Labs called Sentinel, and then maybe also just some of the challenges of trying to think about moving machine learning to the edge. You know, how do we stop moving all the data to the cloud and start moving the machine learning to the device? Cool. Thanks so much, Sam. We're really excited to have you. Go ahead and try and share your screen.
Sweet. All right. Let's see. Okay, can everyone see my presentation?
Yeah.
All right, fantastic. Really excited to chat with everyone today. As Sarah said, I am from Conservation X Labs and am project lead of Sentinel AI, which is really about trying to do on-device computer vision for wildlife conservation. Just very quickly, a little bit of background on Conservation X Labs and what we do. Two things. We run prizes and challenges, which is what we call open innovation, where we try to get many innovators involved to address some of the major problems within, or technical holes, I guess, within conservation. And then we also do what we call directed innovation, which is where we develop engineering projects in-house with the intention of them becoming sustainable companies, spin them out of the nonprofit. We've done one project that is a handheld genetic diagnostic tool designed for field use. It was actually involved with some COVID work, and the idea being that anyone can use this device in the field. And then the other project we've been working on is called Sentinel, and that's what I'm going to chat to you all about today. I think just take a step back with this. When we started this project, initially it was going to be a next generation camera trap. And so when we started to try to scope the project, we were trying to figure out exactly, what we were building. And I think, I'd like to, obviously, these are some of the things that came out in the interviews. There is a lot of work in this space. A lot of the work actually that Sarah's been working on addresses a lot of these issues, but, there are lots of people out there working on this. But the things we consistently heard is that processing costs a lot of money and it takes a lot of time. We often have people that have hundreds of trail cameras, and then turning that into something, meaningful as far as an action, a conservation action, takes a lot of time. There's also often a lot of bycatch or useless data we hear, a lot of false positives, non-target species. There's also a problem of missing time-critical events. So for scenarios which require an immediate reaction, things like poaching or the reintroduction of invasive species or human-wildlife conflict, often we get that data right now after the bang, as we like to say. So, the elephant or whatever has already been poached, or there has been a human-wildlife conflict, but it is only known after the fact when the SD card is retrieved. We'll also hear a lot about data retrieval being a real problem. So retrieving SD cards from the field is difficult, or the technology may not work in the region. And then we also hear that, powerful tools are out there, but perhaps they're outside of the technical or financial reach of people that are working on the ground. So the Sentinel really is trying to be a low-cost solution that reduces time and effort of going from data to action. And so we do that by having hardware that runs user-specific AI on existing monitoring tools. And so there's that GIF on the side there, basically showing how it works. This is an early prototype we developed from a few years ago actually now. But basically, we try to retrofit those devices by kind of going into the SD card slot or a USB port and augmenting that device, that data logger into a smart device. There's also cloud software that allows people to create, manage, and use models. So what we do is we have, again, this hardware that is an adapter that gives any trail camera AI capabilities. It's really doing three things. It pulls images from the monitoring device. It processes those images with a user-specified edge AI model, and then it communicates those results to the user. Those three steps took a little bit to get there. It actually started with a whole bunch more things in the process, but we've got down to those three basic things, and that's where we feel like we can provide the most value. And then I think it's important to recognize although we are doing edge AI, it's only really useful if we can, manage it in some way. So we do have some cloud software as well that allows that management of those edge devices. So it's what's called fleet management. So if you have 100 camera traps out there, and you want to, see what's going on with their data, deploy new models, change the settings, those kind of things, that's all managed from the cloud. And then if you want to create new models and deploy them, we have kind of set up the cloud side of things to allow that communication to the edge. As far as like what we do with the AI on board, these are some of the examples of the algorithms we've been working on recently. So the majority of our work is around species detection or species classification. We do a little bit of work in bioacoustics, which, isn't necessarily computer vision, but, during the pre-processing of acoustic files, you tend to turn them into images and then process those images. And then we have also been doing a little bit of work in behavior analysis or video analysis to detect behavior of animals in the field. So this might be self-evident, but I did want to kind of run through how this works in the field when we have something out there running a model on device. And then hopefully that grounds some of the conversation we'll have in a second. But basically the data is captured on a camera trap, a trail camera, whatever you want to call it. We're also doing some work with acoustic recorders, but the data is pre-processed. So the image might need to be resized. If we were doing grayscale models, we may have to obviously transform that RGB image into a grayscale image. And then we do run a model on the device. The results of that model are written to memory. If we are doing a two-stage setup, a two-stage model where we might run an initial model, and then depending on the output of that first model, we might run another one. A scenario where that would be true, for example, we recently put Megadetector on our device, where it's a very trusted algorithm, but we might want to do a species classifier on the output of Megadetector. And so we might, once we do all the AI, if there was an event that was of interest to the user, in that kind of from that cloud programming perspective. So when we have our management dashboard, if people find if someone sets that they want to get notified of that event, we then start that process of getting it back from the edge to the cloud. So the interesting thing here is that, if you have the bandwidth, you'd like to also send a little bit of information about what was going on in that image. So a thumbnail, the image if possible, you'd be nice to send that back. So if you do have high bandwidth communication, so like Wi-Fi or LTE, we'll send both the data and the insight. But if we don't, we will just send that metadata back. So basically we ran algorithm 423, and this was it came out as predicted of, class number 2. with confidence, 69. And then we would have stuff on our database that would be able to turn that into something meaningful for people. But basically, it's a very short message that can get out very easily via things like LoRa, satellite, or 2G. Again, and then if it's programmed so that people want to have an immediate notification, get a text message, email. Otherwise, it just goes into the stats that would be viewable through the cloud portal or just a weekly email. So now that I've kind of, in many ways, that felt like a little bit of a sales pitch, which I'm trying not to do in this talk. I'm going to quickly run through the approach we take to AI, which again comes to the lens of trying to get AI on device and get those insights back out to users that are, not necessarily anywhere near those devices. I think the very first thing to think about is, you have to frame the model. And this is a kind of a non-trivial thing. I think, we have to really think about, in our case, models answering a user question. And so framing that question is actually very important. So are you trying to count a population? Are you trying to find an individual? Are you trying to catch a poacher? Once you can frame that question and decide what the output of that question should be, the classes, I think you're a long way along making that model. And then you obviously have to have data. One of the interesting things that I think we have the scenario where, we have a lot of people in ecology that have a lot of labeled data. And so often this isn't a problem, but people are often interested in events that don't happen that often. And so if you are looking for, a species that, you've only got 10 existing photos of, and that's, you want to make a model to look for that, we're going to have to think creatively about how to create that model. But I think obviously that data is a precursor. The important question that is comes up because we're running models on power constrained or memory constrained devices on the edge. We need to think about where we're deploying. So how powerful is the device we're deploying to, and that will change the type of model we can run. And then finally, I think just as responsible, users of AI, I think it's also important to consider the consequences of a false positive or a false negative. What we find, at least at Conservation X Labs, when we talk to people, is that people are very concerned about false negatives, where an event that is extremely important may be missed because the model isn't super accurate or super precise. And the other concern being obviously false positives. If we're running into a scenario where we are sending resources out, for example. So if we're sending rangers out based on a report of a potential poaching event, that kind of thing, obviously, if you do it too often, you're going to have a scenario where boy who cried wolf scenario, where the model just begins to not be believed. When we make models, we tend to have small and targeted models. We try to keep the number of output classes to less than 10. And this primarily comes from the idea that, every conservationist has a different question, and those questions can be complicated. So we try to make models that target a very specific, question that the conservationist has. Another big thing that we try to do with our models is we try to explicitly choose creatively negative data. So what I mean by that is that, when we teach a model, for example, to look for, an elephant, we would expect to not only see elephants in deployment, we would also see other animals that are native to that habitat. And so while we may not be interested in them as a class, we may include them as non-labeled blank images or as an explicit or negative or other class. I'm not a computer vision researcher, to say which one is best or the best way to deal with this, but it's something that we have trialed pretty extensively in our work, and tends to make the models in deployment a little more robust. Again, because everyone has a different question, we try to, as much as possible, create repeatable processes. When we make models, we have internal systems that are designed to, reduce the time and cost and technical expertise to create those new models, right through from ingesting the data set from someone to labeling it to deploying that model. This is really important, again, because we're not dealing with unlimited resources and be able to create a model that can run everything. And as you guys are probably aware, during this course, there's a lot of people in this space that are working on this, and we've had multiple scenarios where organizations have already developed a model when they come to us, and they just want it to run on our device. And so we actually spend quite a bit of effort making sure we support major common frameworks that are out there, major architectures that are used, and supporting those on the device. And again, and I'll get into why this is in a second, but this isn't actually necessarily super easy. A little bit of background, perhaps. I'll zoom out here on Edge AI, embedded AI, local AI, whatever you want to call it. I think there's a little bit of a branding issue here as to what we want to call this, but I'll call it for this presentation Edge AI. Obviously, when we're dealing with this stuff, we're dealing with hardware. This slide is from Edge Impulse, which is a group that is really kind of the forefront of putting models on smaller and smaller and lower power devices. But recognizing that there are limitations to what you can do on certain types of hardware. So when we work, typically we're working in the image and video space. So we are really, right now, this may change in the future with advances in hardware and AI. We're currently running CPU and then dedicated CPU plus what are called GPUs or VPUs or NPUs, which are basically chips that are designed specifically to run models very efficiently. While you might have a lower power footprint overall when you're trying to use, a microcontroller, for example, over a CPU, ultimately running that model may actually be less efficient because it's not designed to run, tensors or convolutions. And so I think one of the really exciting things in the space, and I think it's still maybe a little bit away, a little bit far away, but there's been some announcements from places around dedicated low power edge AI microcontrollers. For example, the ARM Cortex, the ARM U55 and U65 series are really interesting because it really means you can start to think about really low power edge devices. This may be, again, self-evident, but we are only doing inference, meaning only doing predictions on the edge. I'll put a caveat here saying that some on-device learning is possible, but we currently don't utilize it. So all the training, managing the databases, all the device management, they still occur in the cloud. It's basically just deploying to the edge and then running that model out there that is in a way that's not connected to the cloud. If we're looking at like a pro and cons list of why you'd use edge versus just running things on the cloud, the very first thing I'd mention is that if you're running things on the cloud, but you have something out there in the field, you need to have data streaming communication. Now, this may be possible in some scenarios, but often where we deploy, it's either very little or none, no cellular connection. So this is just not really possible. So what I view Edge AI as in many ways is a kind of front-end data compression. basically turning an image into, 10 bytes that allows you to send that information or that metadata back via whatever communication you have. And in our case, it often ends up being satellite. You often see other industries mention these last two, so privacy and latency. Privacy is obviously important in our scenario for a lot of use cases around things like poaching, but it doesn't play in as much as other people using Edge AI. And then latency is very important for things like self-driving cars. Obviously, we're not in that space, so it doesn't play in so much, but that's another reason people use Edge. The cons are inherently that you are limited by the hardware you run on. So you can't just use a super powerful computer in the cloud, or even your, a laptop that is connected to the cloud. It is inherently limiting. We have to also consider things like battery life and then the limitations of the type of model we can run. So the memory of the chip you're running may limit the type of model you can run. And then there's also, and I'll get to this in the next slide, the operations that are happening, like the mathematical operations that are running inside the model. Some of those may not actually be supported by the hardware, or at least not easily supported by the hardware. The other con is that you have to deal with the hardware, which tends to be expensive and then actually a big time suck. You spend a lot of your time just trying to get things to turn on. In fact, last year I spent a couple of months just trying to turn on our hardware because it was just stuck in reset mode and not turning on it. And that kind of thing gets relatively frustrating. Again, this is our setup, but I think there are a number of ways you could do this. We chose to use Google Coral, which is a product from Google, which is dedicated to, being a very efficient processor of AI algorithms on the edge. There are other similar products from NVIDIA, like the Jetson. Intel has chips like the Movidius or Myriad chips. So there's a lot of options out there. We chose this setup specifically because it's low cost. It's powerful, meaning we're not limited by the types of models that can run. And then because it has this dedicated, what Google calls TPU, tensor processing unit, it's very efficient at running models on a per energy basis. So we can run some pretty large models, but not burn a lot of power doing it. The big con is that this is not something you can run all the time. This is you basically, if you ran this all the time on a battery, you would have a pretty short deployment. So what we do to get around this is that we actually have a microcontroller controlling power to this system. So we have it set up so if the camera takes a photo, the camera trap takes a photo, the microcontroller can turn on the power to the system, and that image can be processed quickly, and then the device turns off as quickly as possible. I think this is another diagram. This is how Google describes the process of getting a TensorFlow model onto the Google Coral hardware. So I think it's important to recognize there are a number of steps to go from the model you might be dealing with in the cloud or on your laptop and putting it on device. Each of these steps have little pitfalls and limitations. And so one of the lessons we've learned is that the first thing we do is make sure we can map or basically compile the model for our hardware. For example, in the past, we used some of the YOLO algorithms, and until recently, it was very difficult to put YOLO algorithms on Coral, just because of the operations that were going on inside those models. But basically, you train your model, you export it, and then you're converting it. The big thing that happens when you convert it to a TensorFlow Lite model is that you are what's called quantizing the model. You basically making it smaller, and I'll get into that in a second. And then once you have that TensorFlow-like model, you're then compiling it specifically to run very efficiently for a edge TPU, which is on the Google Coral. Basically, the big difference between an edge-based model and a cloud-based model, I would say, in practice, is this quantization step, which again just kind of takes a really big your weights being really big numbers and putting them into relatively small integers, and so what that does is it reduces the storage size, uses less RAM, it has less latency. But more importantly, the hardware often only supports, operations that are quantized. And so this typically looks like 2 or 3 lines of code. It's not a big deal, but it is amazing how much time you can spend trying to get your model set up to accept this if you're not using a traditional kind of off-the-shelf model. Or some example code. So just a heads up, if you are trying to use your model that you've created and putting it on the edge, if you've used kind of standard architectures, you're probably good, but no promises there. The other thing you see a lot in the space is that you do something called pruning, which reduces the size of the model by basically cutting out the unimportant connections between nodes within the neural net. And this is really helpful, again, if you're trying to get a model onto a really small device. So we're not so limited on the Coral, but if you were trying to get your model to work on a microcontroller, for example, and we're trying to get the model to be as small as possible, you can prune your model. I just wanted to show this because this, I think, maybe illustrates what I was talking about. Again, this big problem of the big difference, I would say, between a cloud-based model and an edge-based model is that you're just limited what you can do on the device. So, we did some behavioral models recently that were, very state-of-the-art models we were taken from other people and we had to remap and re-architect some of the models to run on the device because they couldn't do 3D convolutions on the Google Coral. And so there's just little things like that you have to be aware of. And one of the things we do now when, for example, we're working with new people that want to, bring their models to us. For example, we've had discussions with WildMe recently who do individual re-identification. And the very first thing we do when we have a look at whether we could put their models on our devices, we run through the model architecture and actually go into see what mathematical operations happen within the model so you can see whether it works. There are often ways to get around the issues. You just would switch out an operation and there are often, there's a lot of help on things like Stack Overflow as to how to make that work. But we see the most issue when you're converting between frameworks. So if you're, for example, doing your work in PyTorch and then you're trying to obviously port it over to TensorFlow Lite, that process of converting often introduces operations that may not be supported. So it's just, again, something to consider when you're setting up your workflow. In some ways, this slide perhaps doesn't illustrate my point well enough, but I'm sure this has been hammered home to you all, that the scenario of doing AI for wildlife conservation means that you're dealing with data that is nowhere near as clean as the data you'd see in a typical, baseline data set, a data set that is used to kind of tell how good a model is. And so you get a nice clean image like the one on the left in the COCO data set, but in reality, you're getting motion blur, you're getting night photos, you're getting occluded objects. Sometimes, obviously, you'll get photos of animals right up against the camera lens. And so I think the point here is that the model has to be pretty good, and in reality, it's not going to perform as well as kind of those example data sets you see online. And so as much as possible, we try to lower the expectations of what people expect of models, just because it is, so difficult to do what people are doing, in terms of spotting animals out there with the cameras we use. This is the last slide on this, but keeping up with AI is really tough. During the project, we've had to do a number of different things that have really caused headaches. The big one being we transferred from Tensor 1 to Tensor 2. That really sucked. And so these kind of things tend to take a lot of time, but we had to do this to kind of keep up with the dependencies of the hardware. And that's one thing that I think is worth mentioning, is that the hardware often is very limiting, for edge-based stuff in terms of, the dependencies or the types of environments you can set up. And so what we do is we try to not change too much, but when it's necessary, we will. We recently started working in PyTorch a little bit more, but whenever we do now, we actually try to, we might experiment in PyTorch, but then if we're implementing a final model or a final training pipeline, we might translate that PyTorch model into TensorFlow just for simplicity's sake. In terms of how we deal with all this stuff, we've had problems with different computers not working with things. So we use environments in Docker containers as much as possible, just to keep everything the same, because things break when you're using different types of systems. And when we choose to add a new system to our kind of architecture, we try to choose the most up-to-date and systems that have the most long-term support. Because we've been burned, for example, just very simple, choosing to use on our device, we chose to use a Linux that meant you were running a very I think it was like Python 3.5, and basically within a year, that support for that version of Python started to fall out of favor with the libraries we were using that were super necessary for what we're doing, and so it meant that we had to again update our system. And then wherever possible, we use standard protocols because that's what the community uses, and it means that we can just move through our systems without, if we have to update, they tend to be one of the standard protocols whenever we change systems. I mentioned this earlier, but I think it's worth reiterating. There is a huge focus in the space whenever we talk to people on false negatives, meaning missing data that is important to users. It is the #1 question we get when people ask us, oh, how good is the model? They're interested in recall specifically. So how will it pick up the event that I'm interested in? And so one of the things we've used to deal with this is that, again, there are certain algorithms that are trusted by the community. Megadetector is one of those algorithms. And so for scenarios like this, where people are really concerned about missing images, we'll actually implement things like Megadetector on the device just to make sure that people's kind of fears are alleviated. I do want to mention this, that Edge AI, the model is just the beginning. I'm going to kind of skip through the slides pretty quickly, and I'm happy to revisit them if people are interested in them. But basically, there's a whole system that goes into making an Edge AI solution. It's just this top left that is like the Edge model running, but you have to train a model. It's got to communicate with a database. It's got to deal with communications, and you got to have a feedback loop. And so, again, not going to get into this, but if people are interested, I'm happy to go into it further. When we train a model, we use Megadetector as an auto labeler. It's been a fantastic way of accelerating our way of getting new data into our systems. We have auditing software that allows us to constantly enrich our data. So we're not only tracking taxonomy, but things like behavior, the sex of the animal, the life stage of the animal, so that when people want to make an algorithm, we can start to offer different types beyond just species identification. The big thing here, again, I'm going to run through this pretty quickly, but we may we try to like containerize our processes, meaning that we try to keep the input and output of each stage of the process of making a model very standard. So the what we'd expect into the model is into the training pipeline is this, and what comes out is an edge ready model. And by doing that, it means that we can change what goes on inside each internal little process of training the model, each little process of doing that. But if we change a little thing, or if we choose to, for example, we've been using a little more of Edge Impulse's platform recently, which is a company that does Edge AI. We can switch that into our training pipeline or our model pipeline, but we can switch it out just as easily. This is a quick example of our auditing software we have in-house. What we tend to do when we ingest a data set or we get data back from the field is we quickly have a look at it very rapidly. We would provisionally accept data if it's above if we audit 5% of the data set and we think it's performing at a certain level, we may accept the rest of the data as assumed to be correct. We have had problems with this in the past, but it's a way that we can very quickly deal with large data sets. This is a relatively small data set in many ways. We've got from Ocean Conservation of 30,000 images. We sometimes, for example, we did something with the Nature Conservancy a while back, and that was 10 million photos. So we only audited obviously a subset of the model. Very quickly on this, communication, kind of a parallel to that classic quote. If a model processes an image in the woods and no one receives the message, did the model run at all? Communication sucks when we talk about doing stuff out there in the field. It's very complicated. We're often dealing with different countries, dealing with scenarios of we're in the middle of nowhere, so don't have great cell coverage. We're under the canopy, so even getting satellite signal tends to be tough sometimes. So we spend a lot of time thinking about it. And the reason why communication is important for Edge AI is that updating models relies primarily on a feedback loop. So if you can get data out of the field, so if you can get even little thumbnails out of the field, a human can provide feedback to whether the model is performing well. And so, like that pops up on our dashboard, very similar to this here. So basically, we just have a little audit when it's, if the model needs to be retrained because it's not performing well, this feedback loop allows that. The other thing that if you can have communication with the Edge AI device, you can do that over the air model update. Unfortunately, for a lot of our scenarios, and it's not something we've solved, is that even small models, so some models that like in the acoustic realm where you're less than a megabyte, and then even in some of the smaller image-based classifiers, it's very difficult to get that data through low bandwidth comms like swarm satellites, which is what we use for our satellite communication, because basically those things like swarm or LoRa based like long distance communication, you're basically sending text messages. So you don't have a connection to the internet in the same way like even like a 2G mobile might be able to connect. You're really dealing with a scenario where can you text what you need to get out. And so when you do it like that, you don't have this ability to do communication. What we use on the Sentinel, again, this is not the answer to this, but what we do is we have two options. We have cellular and satellite. They work globally, which is nice. They're modular, so we don't have to put them in our device, which saves costs. But the big requirement is that a two-way communication, so you can do both an upload of data, but you can also change settings and do a download of data. The big thing we chose these for is because they both have low cost, because ultimately, if you have 100 devices out there and it costs you $40 to keep your satellite per device online, very quickly that bill racks up. We ran into the problem of communication being an issue very recently in Costa Rica. We expected to have 4G actually out of this research station we were working on. It turned out the 4G we expected to be there was the wrong band to what we were expecting it to be. And so reality, we were dealing with a 2G scenario. And as you can see, we were working down on this part and there was no cell coverage. So this deployment turned from a LTE or like a very high bandwidth connection deployment, which is really nice for doing like model updates and things like that, to a satellite deployment. These are the kind of realities of being on the ground. And then the other thing I'd mention with all of this is that while this looks like there's a lot of coverage, when you get on the ground, it's amazing how quickly you'll walk out of coverage, even in these areas that are not great, that look like there's a lot of coverage. Hardware. Inherently, again, because you're working on the edge, you're dealing with hardware. Hardware, as they say, is hard. And I would add the caveat that it's expensive, both from you have to make your stuff, but it's also it takes a lot of time and effort to make it work. If we were to say the number one question we get for hardware, and this goes for anyone that's interested in making edge AI hardware out there, the number one question we get every single time without fail when we talk to a potential user is, how long does it last? It's what we try to say. Our goal is that we will last as long as the camera trap is attached to. But as a result of this requirement, Sentinel chose to not be always on, because if we were always on, we would have to have a solar charger. That requires you to have very consistent sun. If you're under the canopy, which is often where we are, you don't have that possibility. So I think when you're, doing your battery calculations for how long things will last, idle and boot tend to actually be most of the power drawer. If you're smart about your actual processing, the AI, and so choosing a system that can be very low power most of the time is really important. When you talk about the power footprint of of running models, loading images and loading the model is actually a big part of that power. And then finally, obviously, you have to deal with communication and also budget that into your power requirements. How much does it cost is the second question we get asked all the time. And if that number is too high, the conversation is over. And so we try to, as much as possible, have a low-cost device, low-cost subscription, and then scalable pricing is really important. Meaning that, if you're going to do a subscription-based, where you have to have cell coverage or whatever, or satellite coverage, if we've had price models where if it's like $40 per device per month and you do the calculation on 150 devices, very quickly that is a lot of money. And so if possible, trying to make sure that you can deal with that. As I mentioned this earlier, there's a lot of movement in the space, both from the hardware perspective, getting better at processing models, and models becoming smaller or more accurate. Getting smaller without accuracy trade-offs. This is actually a model we tried very recently called FOMO from Edge Impulse, and been really impressed with it so far. But basically, this could fit on a high-end microcontroller, which actually opens up some possibilities for doing, for example, always-on monitoring and running this on an Arduino, for example. I was kind of shocked how good this performance was, to be honest. When we make things, it's interesting how our solutions tend to get simpler rather than more complicated. It's actually a little thing that I've noticed on both of our projects we've done at Conservation X Labs is that we kind of start off with something that is, a very complicated version of what we end up doing. So we initially were doing a full-on camera as well as the processing unit. We heard a lot that people were interested in things like trigger speed and night vision, like performance at night. And we just weren't that good at doing the optics for things and making things wake up fast enough. So we really just started to focus on only doing the edge processing. And that was what this device was. This was a prototype. We also had a communications backpack for a while where you would aggregate data through, like a single system from a bunch of Sentinels deployed out there. That this Sentinel backpack or the communications backpack failed. And so all of those devices kind of went offline. So we learned very quickly to put all of the communications in the device, which is where we arrived to today. Under the hood, if people are interested, basically when we're doing our prototype, you can do this, relatively quickly, I think. But we were using a Raspberry Pi. We were running the models on the USB dongle version of the Coral. We had a cellular USB dongle as well, which provided the communications. And we used a little trinket from Adafruit, which is this little microcontroller that was doing all the power cycling and control of power to the kind of more high power parts of the system. And this worked pretty well. We could get, 30 days battery life out of this, and we had this out in the field for a while. The big problem with something like this is that you can't make a lot of them, because I was doing all the soldering for this, and it was like 200 solder points, I think, on this device. And very quickly you get sick of doing that. So we moved towards what we're calling our beta product, which is designed really, not necessarily, it's more reliable, but the big difference is that we are more manufacturable, so it's much easier to maintain the device. Just to finish up, I was going to show some example deployments we've been working on. The first one was this work we've been doing with the Nature Conservancy in Virginia, in the USA. Basically, there are some very acute threats to nesting seabirds out there, specifically oyster catchers. There are coyotes getting onto the coastal islands they're on, which is obviously something you'd want to notify the land managers about. And then there's also these, due to rising sea levels, more common to have what are called washover tides, where basically these seabirds are nesting on very low-lying land, and those eggs get washed away if there is a high tide. So they are interested in understanding very quickly about what's going on. They're also doing, how they set up the study is they have, getting a picture every 15 minutes, and they have 200 cameras out there. So I think there was, in a season, they were getting 10 million photos. And so even any way we could help them process those images more quickly was helpful. Doing a little bit of work in the Osa Peninsula in Costa Rica, which is really around about trying to monitor ecosystems at a kind of at a large protected level, a large protected, national park level kind of area, focused around jaguars. They're predators and they prey. The predators mainly being humans and hunting and poaching. So we have a model that is looking for hunting dogs, and then a model that's looking for the jaguars and their main prey species, which is the white-lipped peccary. You'll see this a lot in Edge AI. I think this is probably the easiest sell for us, which is the rapid intervention of human-wildlife conflict. This can be poaching. This could be, dangerous animals or nuisance animals in areas. But basically, we're planning on doing some work in Mozambique at the Gorongosa National Park around elephants. So rapid notification of presence, integration into deterrence technologies. I think this is very interesting because you could do this without a human in the loop. So there's a lot of techniques used to keep elephants away from crops, for example, And so integration of AI to immediately set off those deterrence technologies is interesting. And then obviously rapid notification of potential poachers is something we've also been working with them on. I've got about 10 minutes left, but I just want to quickly run through what I think is kind of the state of the art for what you can put on the device, like the Coral. And I think that really gets into this idea of, behavior, welfare, and disease, which is mainly in the video processing space. I'm going to quickly skip through this, but basically, you see this a lot in humans type stuff. Human action recognition is used a lot in sports. You see it a lot in neuroscience. I believe there's a lot of people working in this space. The Mathis labs at EPFL are working on Deep Lab Cut, which is doing similar stuff. We actually got a postdoc to work on this specifically around behavior monitoring. And so I showed this mainly as a demonstration of what is possible on the edge if you have a system like the Coral. But basically, we can run all of this on the edge, and it's basically what I would call the limit. So doing anything more than this is really tough. This doesn't run in real time as well. So basically, we can run object detection or segmentation, where you track individuals. You would then classify each frame of that track. You can also do what we call a flow generator, where you're seeing how that animal moves through time throughout the video. You join them together with what's called a sequence model, and then you output a behavior. And this is really interesting, I think, because it opens up the possibilities of what you're doing as far as monitoring behavior or welfare of animals. What that looks like in the end is something like this. I mean, a very, very basic example. But I think, ultimately, as I said earlier, algorithms answer questions. We need better questions in the space, and we're starting to get them. We've seen some people approach us around wildlife disease. But if people out there are interested in chatting about this further, I'd be really happy to. We found that object detection was sufficient. We initially started with segmentation, but object detection is obviously faster and was actually just as performant. I showed this as well as just another example of what we're doing. This is kind of a sidebar, mainly because we are working on there's a demonstration project, but this is detecting lameness in animals. And so you can see that we can detect lameness in cattle in a milking shed. We mainly use this as an example because the data was out there and an open source. But again, hoping to find some more data to be able to detect things like this in wildlife. And I'll leave that there, and hopefully I've left a couple of minutes for questions.
Thanks so much, Sam. Who has a question? Yeah.
Hi, really cool talk and awesome work, super interesting. I am just curious about the organization as a whole. Is it run as like a startup or as a nonprofit? And you mentioned like the OSA Conservation Center and the Nature Conservancy. So how does it work? Do these conservation organizations come to you guys with specific projects, or do you guys also just like play around with certain tasks that you come up with?
Yeah, it's a bit of a mix. So on that first question, we are set up as a US-based nonprofit. It is possible to spin a for-profit out of a nonprofit. I don't get into that much. To be honest, that's like starting to get into some legal space. But basically, the intent is that we develop the technologies. We believe that if the technologies can survive on their own as a business, we'd like to do that. And there would be for-profit companies, but typically we set them up as a B Corp, which just means they have they're mission-based. As far as how we interact with customers or users or however you want to call it, they typically come to us, or we do some kind of we're connected in some way. But yeah, usually we get those people to come up with the algorithm themselves, as far as framing exactly what they want out of the system. But for example, OSA conservation was a mutual connection we had through Adrian Forsyth, who works in the Amazon and had done a little bit of work with us in the past, and he founded OSA Conservation. So, it's all a kind of a network, and making sure we're out there just being visible.
I had a question related to the cameras that you work with. Super cool to see the technology integrated with all the different cameras. I was curious if you run into any issues across cameras made by different manufacturers like Reconyx or Bushnell, and with those also kind of changing throughout time, with the devices improving.
We do run into some problems with some brands, in all honesty. The common ones we don't. So Reconyx, Bushnell, Browning tend to be fine. We have run into issues with so SpyPoint tends to be a bit of a problem because they use micro SD cards. And so right now we're currently going in through an SD card slot. We also run into problems with things like cutty backs or anything that is a kind of more connected camera and it's doing weird stuff to the SD card. But if it's just a standard camera that is just saving files like you would like a point and shoot, DSLR or whatever, those tend to be fine.
Any other questions? Tiziana? Yeah.
What is the difference in cost between the satellite antenna and the cellular antenna?
So initially it was going to be a lot, if I'm being honest, but Swarm is kind of really changed the game for us as far as satellites. So I think Swarm costs about $99 right now. It's about $100, and then just to buy the device for us, and then it costs about $50 for our cellular, 50 to 60 depending on the configuration. The cellular is very advantageous is that the per month cost of the device is like cents versus the satellite, where there's just, if you use the device at all, it costs $5 per month per device. And that's kind of a flat fee. And that's pretty good, to be honest, for satellite, like compared to Iridium, but you'll see that that's very quickly where the cost goes is into the subscription type fees.
And how often does the model run? Does it wait for a few, like a batch of photos and then run? Because it's not open all the time, right?
Correct. That's just kind of how we've tried to set up the system. That is programmable within our settings. So if you want to process things immediately, so if you want real time, it will process every time a photo is saved to the memory card of the trail camera. But we can also set up, for example, we've actually found that people want near real time, but they don't actually want, or don't need, I should say, to the minute real time. And so often people will only want a daily download. And so we'll wake up every 24 hours if there was a photo taken, and those photos are basically held in queue on the SD card. And that really extends the battery life of the device, doing it that way.
Yeah, go ahead.
And as a user, which output would I be getting? What's the format of the output I would be getting?
So if you're using it, again, depends on how you get, how you send the data back. So if it's just the satellite, you'd be getting, a jaguar was spotted at this time, and we have this much confidence in the prediction. If you had some kind of cellular connection, you'd get that same information plus a thumbnail, or if you request, like a full size HD image. We typically set up like that HD image type retrieval as on a request type basis. So you'd ask for that to be sent through, and we would send that back actually in tiles. So we have to reassemble that image, in parts, in the cloud, and then we'd present that full image to everyone, to the user. So trying to unfortunately deal with the limitations of the communications we're using for getting the data back.
Thanks.
Awesome. Thank you so much, Sam. Thank you again.
Yeah, thanks everyone.
And cool. Yeah, thank you so much for joining. And good to see you.